Welcome back to another video on superposition theorem. In previous video, I had considered two problems where in the circuits we have dependent sources. In both the problems we had to find out the current. In this video, I will again consider two problems only. In both the problems we will have dependent sources, and in this case we have to find out the voltage using superposition theorem. So let's start with the first problem. In first problem, we have to find out the voltage V naught using superposition theorem for the circuit given in figure. The circuit is consisting of two independent sources and one dependent source. This is a current source of 1 ampere across which voltage is V naught, which we need to find out. This is a voltage dependent voltage source where V1 is the voltage across series combination of this dependent source and 40 ohm resistance. Since we have two independent sources, we have to solve the circuit twice. Once when 1 ampere source is active, second time when 25 volt source is active. So let's take first case when only 1 ampere source is active. When only 1 ampere source is active, this voltage dependent voltage source, it will remain as it is in the circuit, while this 25 volt source, it will be replaced by short circuit. So the circuit becomes like this, where in this branch we have a resistance in series with voltage dependent voltage source. Now if we compare these two circuits, both are different. We don't have 25 volt source in the circuit. So when the circuit is different, so obviously this V naught will have some different value. So let's denote it by V naught dash. Similarly, V1 will have a different value. It will become V1 dash, and that will be reflected over here as the output of this voltage dependent voltage source is controlled by V1, which has now changed to V1 dash. We need to find out V naught. For that, what we can do, we can apply KVL in this loop. Usually we say that we don't know the voltage across the current source and KVL is not applicable. But in this case, V naught is already given as voltage across the current source. So there is no issue. We can start from V naught as negative sign is coming first. So minus V naught dash. Then drop across this 50 ohm resistance plus 50. Since 1 ampere source is connected in series with 50 ohm resistance, so current through 50 ohm resistance is 1, 50 into 1. Then across a series combination, we have voltage V1 dash plus V1 dash equal to 0, or V naught dash is equal to 50 plus V1 dash. So now we need the value of V1 dash in order to get the value of this V naught dash. For that, we can apply nodal analysis. We have just two nodes. Let's consider this as reference. With respect to that, we will have voltage across this. Now we have the voltage V1 dash across this already. As we are considering this one as reference, so the voltage of this node becomes V1 dash. Now when we apply KCL, in this branch we know that current is 1 ampere. It's flowing towards a node, so it's an incoming current. Let's assume the rest of 2 as outgoing currents. So current through 200 ohm resistance will be V1 dash by 200 plus current through 40 ohm resistance V1 dash minus 0.5 V1 dash by 40. So when we solve this equation, we get the value of V1 dash as 57.143 volts. We had already written the equation for V0 dash where we need to use this value of V1 dash. So V0 dash becomes 50 plus 57.143. So it's 107.143 volts. So this is the voltage across the current source when current source is active. Then we have to solve the circuit once again when 25 volt source is active and 1 ampere is inactive. So let's draw the circuit again. Case 2, when 25 volt source is active. The current source has to be replaced by its internal resistance, and internal resistance of an ideal current source is infinity. So we will replace it by open circuit, and voltage across this was V0. Then we have a 40 ohm resistance over here in series with voltage dependent voltage source, and in series with 200 ohm resistance we have 25 volt voltage source. Since the circuit is again different, so V0 has to be replaced by some other variable. Let's denote it by V0 double dash, and same for V1. Let's write it as V1 double dash, and that has to be reflected over here, so it will become 0.5 V1 dash. Since this current source is now replaced by open circuit, so current through this 50 ohm resistance is now 0. So there is no voltage drop across this 50 ohm resistance. As there is no drop, so the potential over here and over here both are same. This terminal and this terminal, they are same. So V0 dash is same as V0 double dash is same as V1 double dash. Now we need to find out the value of V1 double dash. How can we find out V1 double dash? We can apply KVL in this loop. For that, let's assume that current in this loop or this mesh is I. Accordingly, mark the voltage drop polarity. Now let's apply KVL. Starting from 200 ohm resistance, we will have 200 into I plus 25 minus 0.5 V1 dash plus 40I equal to 0. Now we have one equation and two variables. We can write the second equation as well. From where we can write the second equation? We can write the second equation from here, that the voltage across this is V1 double dash. So V1 double dash, that is equal to 40I plus 0.5 V1 double dash. Or we can even write that 200 I plus 25, 200 I plus 25 minus V1 dash, because this is a voltage across a series combination. We just need to write the voltages of one loop minus V1 dash equal to 0. So from here V1 dash double dash, that becomes 200 I plus 25. So we have different choices that with that we can find out the value of I. Say if I use this value of V1 double dash in this equation, then it becomes 200 I plus 25 minus 0.5 into 200 I plus 25 plus 40 I equal to 0. This will give us the value of I as minus 0.89 amperes. Once we have this value, then by using this equation or this equation, we can calculate V naught double dash, which is same as V1 double dash. So if I substitute in this equation, then 200 into minus 0.089 plus 25, this is 7.143 volts. Now we found two values of V naught. According to superposition theorem, voltage V naught is algebraic sum of two voltages, that is V naught dash and V naught double dash. We got the value of V naught dash as 107.143 and V naught as 7.143. So answer for V naught is 114.286 volts. Let's consider one more problem. Now the question is, for the network shown in figure, find the voltage Vx using superposition theorem. Now circuit is, again we are having two independent sources and one dependent source. This is a dependent current source. Vx is a voltage across this 6 ohm resistance, and it is a voltage dependent current source which supplies current Vx by 2. So we have to solve this circuit two times. Case 1, when only 20-volt source is active. When only 20-volt source is active, then 10 ampere current source, it has to be replaced by open circuit, So the remaining circuit is we have a 20-volt source in series with 2 ohm resistance. Here we have a voltage dependent current source. Let's write this voltage as Vx dash. So the current supplied this by this source is also Vx dash by 2. We need to find out this Vx dash only. You can go with mesh analysis or nodal analysis as per your comfort. I will apply nodal analysis by considering this node as reference, and this one is having at voltage Vx dash. Since the voltage across 6 ohm resistance is Vx dash and we have only one resistance between these two nodes, that is 6 ohm. Now let's apply KCL. We know the direction of current in this branch. For other branches it's unknown. Let's assume them also outgoing. So current through 2 ohm resistance will be Vx dash minus 20 by 2. Current through 6 ohm resistance is Vx dash by 6. Then current through 4 ohm resistance is Vx dash by 2, since we have a current source connected in series with the 4 ohm resistance. So from here we can find the value of Vx dash, which comes out to be 8.571 volts. So it's a solution in single step. In second case, we have to consider when 10 ampere source is active. So case 2, when 10 ampere source is active, then 20 volt source has to be replaced by short circuit. Here we have current source, it is supplying 10 amperes. This one has to be replaced by short circuit. Here we have a voltage dependent current source, 6 ohm, 2 ohm, 4 ohm. Now this voltage is Vx dash, it will become Vx double dash, and that will be reflected over here as Vx double dash. So the current supplied by this source is Vx double dash by 2. We need to find out the value of Vx double dash. Again, we can find it by applying mesh analysis or by nodal analysis. So if we go with mesh analysis, then we have three currents, I1, I2 and I3. And we can write the value of Vx double dash as well. It's a voltage drop across 6 ohm resistance. Since upper terminal is positive, we need the resultant current in downward direction, and that will be I2 minus I3 as per the assumed direction of I2 and I3. So Vx double dash is 6 into I2 minus I3. From mesh 1, we can have the direct answer of I1, since 10 ampere source is connected in the outer branch. I1 and 10 ampere, they are in opposite direction, so I1 is minus 10 amperes. Same happens in mesh 3. From mesh 3 we can have the direct value of I3 directly, that is Vx double dash by 2. So we need to write the KVL equation from mesh 2 only. From mesh 2 we will have the voltage drop across the 2 ohm resistance and then 6 ohm resistance. Across 2 ohm resistance is 2 into I2 minus I1, then 6 ohm I2 minus I3 equal to 0. So this will give us the equation is 2I2 minus 2I1 plus 6I2 minus I3 equal to 0. We can use the value of I1 over here as minus 10. Simplify this equation, 8I2 minus I3 equal to minus 20. So we can say this is our first equation. Second equation we can get by combining the equation of Vx and I3. I3 is equals to Vx double dash by 2, and we had already expressed Vx double dash in terms of I2 and I3, so which is equal to 6 into I2 minus I3 by 2. So this will give us second equation as 6I2 minus 8I3 equal to 0. Now these two equations can be solved simultaneously to find out the value of I2 and I3. I2 is minus 5.714 ampere and I3 comes out to be minus 4.286 ampere. We were interested in finding out Vx double dash. Its value is 6 into I2 minus I3. Let's substitute the value of I2 and I3. Minus 5.714 and minus 4.286. So Vx double dash is minus 8.568 volts. And according to superposition theorem, we have to find out Vx, which is algebraic sum of Vx dash and Vx double dash. The value of Vx dash is 8.571 and value of Vx dash double dash is 8.568. So it's minus 0.003 volts, which is approximately near to 0. You could have solved this problem in the second case by using nodal analysis as well. So this one, they all are at same potential. You can consider this one as reference. Assign one voltage to this node, that will be Vx double dash, and you need to assign one voltage over here. Let's say that is capital B. and then you can write the nodal equation, solve for Vx double dash, you will get same answer. I hope you got the understanding of superposition theorem when we have dependent sources in the circuit. So in next video, I will start with the next theorem, that is Thevenin's theorem.